All right, it says example 7.2, a painter on a ladder. A 75 kilogram painter stands on a 6.0 meter long, 20 kilogram ladder, although in the picture it doesn't mention anything about the ladder being 20 kilograms, tilted at 53 degrees relative to the ground. He stands with his feet 2.4 meters up the ladder. Determine the torque produced by the normal force exerted by the painter on the ladder for the two choices of the axis rotation. Choice A is down here, an axis parallel to the base of the ladder where it touches the ground, and B is over here, an axis parallel to the top ends of the ladder where it touches the wall of the house. So we've beautiful sketch of the situation, 53 degrees, 2.4 up to here. We know it's a 6 meter long ladder, so this portion of it would have to be 6 minus 2.4, which ends up being 3.6. So we sort of look at this as two problems. One problem, treating this as our axis of rotation. One problem, treating that as our axis of rotation. So the first of the two would be, I'll do A first. So if I get rid of everything but what's necessary, we would have our point of rotation, or axis of rotation, our length to the painter, which is 2.4 meters. They call this a normal force, which really bothers me. I wish it was a weight, but they don't call it a weight. I don't fully understand why, even after looking at the reasons behind it, but we'll go with it. It's a force regardless. If this is 53, this has to be 37 degrees. And it would cause a rotation like this, which would be a negative rotation. And it's on an XY coordinate. Mathematically, it's actually not too bad. So our torque at A would be equal to force times a length, but it's going to be negative in this case because it's a negative torque, times sine of theta. The force going downward would be equivalent to the person's weight, so negative mass of painter times gravity times length, sine theta. The mass of the painter, 75 kilograms. He is on Earth with a gravitational field force of 9.8 newtons for every kilogram. To get the newtons, a length of 2.4 meters. And it is the angle between the lever arm and the force, which ends up being 37 degrees, not 53. So sine of 37. If you calculate that, you end up with a torque at point A of negative 1100 Newton meters. So torque has to have a force value and a distance value. If we look at the other situation, the top of the ladder being the axis of rotation, now this would be the length. Length of the painter is 36 meters. It would cause a movement in this direction, and this would be a counterclockwise or a positive torque. The angle between this lever arm and the force is going to be 180 minus that 37, which is 143. Same situation, same way to solve it. We have a torque at point B that is a really aggressively wavy T. It's plus or minus that fourth times the length and sine of theta. I'm going to make another T just because that really bothers me. That's slightly better. So torque at B, in this case it's a positive torque because of the way it would rotate. Still the same force, mass of the painter times gravity. The length has been extended to 3.6 meters. And then sine of 143 degrees. So you end up putting in positive 75 kilograms, 9.8 newtons for every kilogram, 3.6 meters, and sine of 143. Here you end up with a value of positive 1,600 Newton meters. So there is more torque if you look at the top of the ladder as an axis of rotation than the bottom of the ladder. And that would be due to, mostly to, the distance away from that point of rotation.